Now let us extend the same kind of treatment to 3-dimension, because actually the molecules are moving in a 3-dimensional space. So their velocities are also having components in all 3 directions, Vx, Vy, and Vz. And now let us ask this question: what is this differential volume element? And for having the speed in the range v to v plus dv, dvx, and or simultaneously speed vx to vx plus dvx, vy plus vy plus dvy, and vz to vz plus dvx. What is that volume element, and how we can actually integrate it we can get an element which is independent of the direction. So which means actually instead of a circle, it will be a sphere in the velocity space. It's not a coordinate space, it's a velocity space. So as before, you can argue that let us first draw the 3-dimensional space. So I usually prefer to draw the XYZ axis like this. The reason is when you make this correction, you just choose the x-axis and then rotate it along y-axis towards y-axis. So if you just take this axis and rotate it towards y-axis, then your z should point out. So this is known as just like my right hand. So this will be, you can just see it. So from x to y, if I rotate, so z should point out. So that's known as a right-handed rule. If I had chosen it the other way, if I switch any two of them, like if I write x for this and y for this, then it will be a left-handed system. You can easily show it. You can easily realize it. Now, suppose this is an arbitrarily oriented velocity vector, which has velocities along x, y, and z. So the x component of the velocity is if I just draw projection on the xy plane. So and then just draw a line here. So this is the x component velocity, and similarly, would just write it like this. And similarly, this will be the y component of the velocity. So this is Vy, this is Vx, and this is the Vz. So this is the XYZ components of it. And then we are also saying that we went from Vx to dVx. Sorry, it's basically from here we went in this direction. So we can actually draw it slightly separately. So this is the vector, and we went to say, suppose this is the velocity vector, and then what we are doing, we are moving Vx to Vx plus dVx, which means actually in this direction, and then we are also going to Vy to Vy plus dVy in this direction, and simultaneously, so if I just move it that way, I'll get an area element, and then I'll also go in the upper direction to z plus dz, and then I'll get volume element. So that's 3-dimensional volume, where basically this side is dz, this side is dx, and this side is dy. So that is that volume, or if you just write it as dv, is dvx times, this is not dz actually, this will be dvx, because this is a velocity space, dvy and dvz. So that is basically dv, it's a small v, dvx, dvy, dvz. And then we are asking this question, okay fine, that dv we don't want, because we want a dv independent of the direction. So then we can do it in many different ways. It's basically a velocity vector, and then you are sweeping the angle, and then if you sweep it all possible direction, you will get a sphere. In the 2-dimensional, you are getting a circle. In this case, you will get a sphere because you are going in all possible direction. And then you can ask this question, okay fine, I got a sphere independent of the directions, and then I'm just only changing the length of the basically the radius of the sphere from v to v plus dv, and then you can just easily calculate what is the volume content within this. This won't be actually the annular shell thing. Now this will be actually a shell, which is known as a shell. Shell is something like you have a big sphere and you have an inner sphere, which is a smaller sphere inside the big sphere, and this small region which is just lying between this outer sphere and the inner sphere is called a shell. Now, what is the volume of the shell? So that you can easily calculate by all these three methods that I said in the earlier part. So the volume of a sphere is 4/3 pi r cube. So here it will be 4/3 pi v plus dv cube, which is basically the outer sphere, minus 4/3 pi the inner sphere is just only v cube. Again, you can approximate that dv square term and dv cube term I'll ignore. So you can easily figure out that will be 4 pi v square dv, and you could directly ask this thing that okay fine, it is a differential volume of this sphere 4/3 pi v cube, that will directly give you 4 pi v square dv, because you see the integration of v cube is 3v square, the 3 will cancel. And the third thing which will just show you now is okay fine, so I'll go, instead of writing it in the Cartesian, rectangular Cartesian coordinate, I'll go to the spherical coordinate, and then in the spherical Cartesian coordinate I have basically three parameters. One is the length, which is the v, which is just like this, and then I have this angle which I called as phi, which it makes with the x-axis to the y-axis. That was the sense of rotation of positive phi. This is y and this is z. But then I also have another angle, which is basically this inclination angle, which I call as theta. So this theta is called as I think azimuth angle. Now the question is, what will be the ranges of phi and v and theta? V can go from 0 to infinity, but here actually we are keeping the v fixed and going from v to v plus dv. So change it from v to v plus dv. So this is nothing but dv, and then simultaneously we will change the phi to phi plus d phi. So basically if I just draw it like this, so this is phi plus d phi, so that this small angle is nothing but d phi, and simultaneously we have to go to theta plus d theta. That also you remember. dv change I'm doing slightly later. So basically I got some sweep in the phi, and then I'm also sweeping down, meaning I'm going from theta to theta plus d theta. This is nothing but theta plus d theta, and then this small angle will be nothing but d theta. And then if I do that, then I generate this surface, and then simultaneously I'll also increase it in the dv direction. So then I'll get a volume. So this volume, I'm asking the question, what is the volume element? So or the dv for this. So instead of going from dvx dvy vx to vx plus dvx in the rectangular Cartesian coordinate sense, I could have also got a differential element by going from v to v plus dv, by changing the length of the vector a little bit by differential amount, sweeping the vector along phi, which is basically this is a vector, and if you consider this is the plane, and then we are basically sweeping it like this. So this is the phi angle, and then we are also saying that okay, let us also sweep it down a little bit. So that is the theta angle, and if you sweep that way, you can actually generate a differential volume element. Now what is the volume of this? So it is, we can actually approximate to be a rectangular parallelepiped, where actually the volume will be nothing but the multiplication of the length of the sides. So one side is straightforward, this is basically dv, because you remember this was dv. Now what about these other two sides? Now think about it, this side, which is here or here, is nothing but here. So this side is nothing but what is this, by the way? So this is nothing but again the v itself, and if this angle is small, So we can write it is nothing but v d phi. So this side is v into d phi. Now what about this side, which we got by sweeping the azimuthal angle? So that you can again see that this is also sorry, this should not be d phi, v into d phi. I'm coming back to it. So this length is v. So let me just write it once again. This is v, and that I'm sweeping, this theta I'm sweeping by d theta. So if this is v and this is d theta, so then this will be v times d theta. Now let us calculate what is this, what is the change due to the change in phi from phi to d phi. So that we took a projection on this plane, which I'm writing once again. Now look at it carefully. Now what is this angle? This angle is theta. So this angle also should be theta, because this is the z-axis and this is a perpendicular to the xy plane. So these two lines are parallel. So if this is theta, this angle also should be theta. So if this is theta, I know that this is v. This is the length of the vector, velocity vector, which is just the speed, the magnitude of the velocity vector. And then if this is theta, this is nothing but v times sine theta. And then what we did is that this v sine theta, now we swept and got something swept along this axis. And this sweeping is, so if you remember, this was my x-axis, this was my phi, and this was my d phi. So this is the small d phi thing. So what will be this arc length then? This arc length will be nothing but the length, which is v sine theta, into d phi. So this is this already we showed, it is v d theta, and the other side, which is this side, is v sine theta d phi. So if I just multiply all these things, one axis was, so this differential volume element is, should not write it as dv, or I can just write it as d capital V, something like that. So that is, here also I should write it as d capital V, the volume element. It is v to v plus dv, so that is giving me one side as dv. Theta to theta plus d theta, that is giving me one side as v into d theta. And phi to phi plus d phi is giving me v sine theta d phi. So what I'm getting is v square sine theta d theta, sorry, d phi, and there is also a dv. Yeah, so I'm just collecting the terms. So now I have to integrate over theta and phi. Because I'm just keeping the length same, I've done an incremental change and I'm doing a sweeping along this any direction, and that will give me the volume of this spherical shell. Shell means it is just the just that structure that lies between two concentric spheres. Now what it means is that the that volume will be nothing but integration over this thing over changing the theta from 0 to something, the phi 0 to something. Now phi integration is always 0 to 2 pi, as you have seen, like we just saw in the two-dimensional case that phi is basically all this angle. Now theta, how much you have to change? That's the question. What we are doing, think about it, it's basically a sphere. And at the center I have x, I have y, and this is z. Now I had a vector like this, and if I sweep the angle phi, I'll generate this thing, and then I'll sweep the theta also in this direction. So if I sweep the theta, I'll get another circle. I'm sweeping theta and phi together. So that way I can actually generate the entire surface if I sweep the theta all the way from here to here, which means the theta variation is nothing but from 0 degree when it is aligned along the z-axis to all the way to minus z-axis, which is basically 180 degree or pi. Now this picture you have seen in geography, just like these are my latitudes and longitudes. So latitudes has basically have 0 to 360 degree or 2 pi, and longitudes have 0 to 180 degree or pi. So that way you can actually construct the surface of a sphere. Exactly the same concept we are using here. So now if you integrate it, this v comes out of the integration. It is v squared dv. So there is no v integration. And then integration over sine theta d theta is basically minus cos theta, evaluated between the limits 0 and 2 pi. So you can easily ask this, minus cos theta evaluated between 0 and 2 pi, sorry, 0 and pi, not 2 pi. And integration of d phi is just phi, and the limits are 0 to 2 pi, so that is giving me 2 pi as before the circle two-dimensional case. So cos theta, cos 0 is 1 and cos pi is 0. So it will be basically minus of 0 minus 1. So it is 1 only. So what we will have is nothing but, sorry, cos pi is actually 1, minus 1. It is always better to remember it in this way. So you have pi by 4, pi by 2, 3 pi by 4, and pi. So cos actually is plus 1 when it is pi by 4, when it is 0. So then actually let us just draw pi by 2 and pi by pi that way. Yeah. So it is 0 at 90 degree, and then it is minus 1 at pi, and sine will be basically 0 at 0 degree. It is plus 1 at pi by 2. It is 0 at pi, and it is minus 1 at basically another pi by 2 radian, which will be pi plus pi by 2, so 3 pi by 2, something like that. And at that point cos will again come to 0. So this is the cos curve, this is the sine curve. Anyway, so cos pi is nothing but 1, sorry, minus 1. So this integration will be times, minus sign is there, minus 1 minus 1, because cos 0 is plus 1, but it is the lower limit of the integral. So that will give me actually 2 factor. So this will be nothing but that 2 and that 2 pi I'm writing as 4 pi v square dv, which is exactly the same value we are getting whichever way you do it. So I showed you 3 different methods for calculating the differential volume element in basically in 2 dimension first, and then in 3 dimension. And we showed that the 3 dimension one is the one which we need. So then the question is, we know that there is a fv, or which we already calculated. So fv is nothing but this function, which is this. Fv is a cube into e to the power minus bv square, and then we are multiplying by a volume which is basically independent of the direction. So that differential volume we are adding, multiplying, because then we'll get a probability. And then if you integrate also over all the velocities, then we'll get actually, it is a probability distribution, so that should give rise to 1, which means if I take now fv and multiply by the volume element 4 pi v squared dv and integrate it over all the dv range. dv range should be 0 to infinity. It is not minus infinity to plus infinity, because vx can, or vi or vz can go from minus infinity to plus infinity because it's a velocity, so it has a direction. So plus minus directions are there, but v is now a magnitude of the velocity independent of the direction, and that's why you did all this calculation to make it that independent of direction what is the value, because all we are interested in the speed distribution, not the velocity distribution. So now if I integrate the speed is just a magnitude of velocity which cannot be negative, so it goes from 0 to infinity, and that integration should give me 1. So that integration will first evaluate in the next section, and then we'll see how we can write we'll see basically how we can get the parameters and how we can get the Maxwell-Boltzmann distribution. Thank you.